We say that a graph is planar if it can be drawn on a plane, on a single piece of paper, without taking a pen off the page and without crossing any edges. So this graph, as we can see, as represented here, is planar. It's drawn on a flat surface and none of the edges cross each other. From this, we've got the definition of a face, and a face of a graph is a region bounded by, well, entirely on all sides by edges, or potentially bounded on the infinite region outside the edge. So here we would say there are three faces. So the three faces here, I can label them as F1, which is the lower, I suppose it's a quadrilateral, but it looks a bit like a triangle, but it's got 4 nodes. F2, which is definitely a triangle, and then F3, which is just the area that's outside of those 2 bounded regions. If we have a finite planar graph with a set of nodes V and set of edges E, if I count the faces and call that set of the faces F, I have this relationship in the cardinality of the sets, that the number of nodes minus the number of edges plus the number of faces for a planar graph will always be 2. So what do we call this theorem? Yes, it's Euler again. He's come back. You still haven't seen the last of him. Well, I think this actually is finally the last of his sneering face. That's Euler's formula for planar graphs. So how would we prove this? Well, it's actually not a particularly difficult proof. If I start with a graph that's drawn in such a way that it is planar, then if I consider just removing an edge from that graph, but not indiscriminately removing an edge, making sure that the graph remains connected. So if I remove that edge is going to merge 2 faces. So removing one edge is going to reduce the number of faces by 1. So if I keep this idea that removing an edge also removes a face, I have that E minus F, the size of those sets, is constant. So if I keep removing edges without disconnecting anything, eventually I'll get back to a tree. And when I get back to a tree, I have to stop, because if I remove an edge from a tree, I will not have a fully connected graph with the same number of nodes. So if I think of this graph at the top, it has 3 faces. When I remove the edge that I've done in dotted now, F1 and F2 both sort of merge into one new face, which I'm still calling F1, but F2 basically ceases to exist. Even if I removed one of the outer edges forming the old F1 or F2, then it would have then merged with the infinite outer region. So it would have merged with F3. So removing an edge will merge 2 faces, so the size of E minus the size of F is constant. So if E minus F, or the size of E minus the size of F, remains constant as edges are removed, then all I have to do is keep removing edges until I get back to a tree, and then count up the number of vertices, edges, and faces. Well, when I get down to a tree, I will have the size of the nodes left, and a tree, as we've already seen, will always have the size of V minus 1 edges. And a tree also will only ever have one face. There are no regions bounded all by edges, there's no circuits, so there is just the one infinite region outside there. So for the case of a tree, I have the size of V nodes, the size of V minus 1 edges, and 1 face. So that's my relationship for a tree. And I can also say that reversing this whole process, I haven't changed the size of V. Yes, I have changed the size of E and the size of F, but when one goes down by 1, the other one goes down by 1. So I'm left with this size of V minus the size of E plus the size of F will always equal 2 for a planar graph.